Assalamu alaikum and welcome to EEE 206 video presentation. The title of our project is Simulating a Small Power Distribution System with Hydroelectric Power Plant. The goal of the project is to simulate several scenarios that are associated with power systems such as load distribution, paralleling operation, and power factor correction on a small power grid. An overview of the power system is given here. The main power source of the system is the two hydroelectric generators and a water level indicator that will act as the source of hydroelectric power. And the system is connected by a high voltage transmission line to a set of residential loads and some motors which will be considered as industrial loads. And finally, there is a backup diesel generator to provide additional power to the system. As the system is too large to simulate at once, it is divided into 5 sections and each of them will be simulated individually. The frequency of the entire system is 50 Hz and the phase voltage is 400 volts peak.
Two MATLAB functions are used as governance systems for the generator. Their task is to keep the frequency and terminal voltage of the generators constant to the system frequency and voltage by increasing or decreasing input power and excitation as necessary.
And here is an overview of the components used in our simulation. The generator, transformers, loads, breakers are essential components that are used in all the simulations. The switch and sliders are used for various switching and adjusting operation, and finally scope, voltmeters and other measuring devices are used for various measurement.
Now we are going to simulate transmission line and generator voltage regulation for different kinds of loads. We are only considering one generator and transmission line for simplicity. Here we can see that the governance systems are adjusting field excitation and input power and thus keeping the voltage on the consumer side to the system voltage and frequency. The system is now operating at steady unity power factor. If we increase the load, we can see a small drop in system voltage and speed. As a result, the governor system increases the field excitation and input power to bring the system back to its optimal conditions. Here, the system is operating at a steady lagging power factor. If we increase the load, we can see a significant drop in system voltage and speed. As a result, the governor system increases the field excitation and input power sharply to bring the system back to optimal conditions. In this case, the system is operating at a steady leading power factor. If we increase the load, the system voltage increases and the speed drops. As a result, the governor system decreases the field excitation but increases the input power to bring the system back to operating conditions.
This is the synchronous generator of our power system. Here we supply mechanical power and field voltage through a governor system. We run the simulation to produce three-phase current and plot the rotor speed and output active and reactive power as well. Now we have to parallel this synchronous generator with infinite bus. For this task, we observe both output voltages of generator and infinite bus carefully. And when their phase shift is nearly zero, then we turn on the switch and notice the changes of all our previous plots. After paralleling, now the generator is supplying both active and reactive power. The speed of synchronous generator, which was slightly higher before paralleling, is now completely matched with synchronous speed. And both terminal voltages are completely matched together. And now we can vary output active and reactive power by varying input power and field voltage of synchronous generator according to our demand, keeping frequency and terminal voltage constant.
In this simulation, we will discuss the parallel operation and power sharing between two hydroelectric generators, and the rest of the system is considered as a simple load. The system has a water level indicator that limits the maximum power output of the governor system. The oncoming generator is set to operate at a slightly higher speed, whereas the running generator operates at synchronous speed. Both field excitations are adjusted to provide the system voltage for both generators. When the voltages are in phase, we can close the switch. As we can see, the speeds of the generators match and are stabilized towards synchronous speed by the governor system, and the voltages are also fixed at system voltage. The twin excitation system allows us to increase and decrease the excitation of the two generators simultaneously. By adjusting this excitation at the same time, we can swap the reactive power supplied by the generators while keeping the system voltage constant.
And now we will simulate a scenario when power demand is larger than the power supply. The water level of the hydroelectric power plant limits the amount of power that the governor system can provide. Also, there is an automatic switch connected to a breaker that is controlled by the power system. In this simulation, the power system is operating near its maximum limit. If the limit drops further, it is impossible for the governor system to maintain synchronous speed. This is undesirable and can cause the total system frequency to drop below 50 Hz. In order to solve this problem, the governor system automatically disconnects the switch and as a result disconnects the top load. By disconnecting the load, the governor system can get the system speed back up to synchronous speed, which is 50 Hz. This allows the system to operate at low input power at the cost of not supplying power to some of their consumers.
Induction motors act as lagging loads. That is why their power factor is very low, and to increase the power factor, a synchronous motor with no load has been used in parallel. The speed of the synchronous motor pulsates during starting and then gradually goes up to W sync. When we turn on the synchronous motor, what happens is it acts as a capacitor and supplies reactive load. As you can see from the graphs, the power factor was initially very low, and when the excitation is increased, the power factor gradually increases and the reactive power consumed gradually decreases. Because of this, the overall power factor increases up to until it reaches 1. And as we can see, the power factor gradually increases with an increase in excitation.
That is all for our presentation. Thank you for your attention.